Blood flow in skeletal muscle serves to supply nutrient to the muscle fibers and to remove metabolism, it controls the tissue growth and atrophy, and also it determines the response of muscle in disease. The reasons for this deficiency is that we are missing a reliable mathematical model that permits analysis of the experimental results. So models are indispensable in modern medical research, which is there are tools that can be used to modify under one framework, and the results will widely different experiments.
Salam sejahtera, my name is Arya anak perempuan Ehput, student ID MH19019. Today I want to talk about what is bioengineering. Actually, bioengineering and biomedical engineering might roll off the tongue similarly, but in practice there are notable differences between the two. Move to the definition of bioengineering. Bioengineering comes from the branch of engineering that they use engineering principles to define and solve problems in biology and medicine. Bioengineering also combination between science, engineering, technology, and medicine to create innovative devices and materials that often related to improve human health. In the field of education, bioengineering covered more broad of topic when compared to the biomedical engineering. That's all for me. Thank you.
Assalamualaikum and have a good day everyone. My name is Wan Siti Fairuz binti Wan Mama Azmi, and I'm going to explain application of bioengineering in blood flow. So the application is about Cisco model. So what is the Cisco model? Cisco model is a subclass of generalized Newtonian fluid which is considered as the most appropriate model for lubricating oil and grease. Cisco model is important due to its adequate description of a few non-Newtonian fluid over the most important range of shear rates. So this is the example of how our blood flows through our bodies as it travels to our heart.
Hi, my name is Adila. My ID is MA19049. So in this video, I will explain about the methodology, which is the step of solution and the concept of our project. So for the step solution, first we need to assume the artery and the Cisco parameter are constant. And then we need to consider the effect of different severity of stenosis, which is 20%, 30% and 40% are investigated in the velocity of blood. Second is stenosis with the severity of 40% is remains, and the radius of artery is varied from 2 millimeters until 5.5 millimeter to investigate the effects of artery radius on the blood velocity. Last step is different types of blood fluids are employed by manipulation of Cisco parameters, and influences of blood fluids behaviors are investigated in velocity profile. For concept of our project, first we need to know that blood is non-Newtonian fluid, which is it is not obey the Newton law. Second is in our project we use Cisco model. Cisco model is actually a blood flow stimulation in arteries with triangular stenosis. Stenosis is actually a narrow section in the blood tube which resulting the reduction of blood velocity. Next is Bernoulli equation, Reynolds number, continuity equation is involved in this blood flow modeling. So in Bernoulli equation, it is stated that no matter the point is located but along the same streamline, the total pressure is equivalent. So when we want to know the blood flow in the blood tube, whenever the point is we want to examine, the pressure is equivalent. So that's why we measure the pressure rather than we measure the velocity, because pressure measurement in the blood is easier than velocity measurement. Okay, that's all from me. Thank you.
For the graphical result, to observe the quantitative effect of the Cisco material parameter, computer code is developed for the numerical simulation in MATLAB. In this study, generally we have taken the delta equal to 0 and the radius of the core is to be 60% of the radius of the tube. Our results are based on the data of two different arteries radius. For smaller vessel coronary artery, the data are chosen as the area is 698.659 over cm cube. The radius is 0.15 cm. For the larger vessel femoral artery, the data are chosen as the area is 32 over cm cube. The radius is
A natural starting point for our discussion of organ blood flow is the microcirculation. In this vast network of the blood vessels, the Reynolds number is generally small, typically of the order. The Wormsley number is also small, so that in the presence of the Newtonian fluid, the velocity profiles are fully developed. So to conclude, one of the interesting characteristics of the Stokes equation is that the solution is sensitive to the details of the boundary conditions, that is, the geometry individual blood vessels and the way they interconnect within the microvascular network.